In this slide, we are going to continue to part 3 for the remaining slides for the subject. Actually, here I'm going to start with the sequential circuit, and as you know, I uploaded 3 videos actually regarding the sequential circuit. So you have to hear these 3 videos before going on with these slides. It's very simple, and as you can see here, sometimes it's a way of dealing with time or with frequency. So I'm going to illustrate what's meant by sequential circuit in the next slides. As I mentioned, the title of the coming slides, actually you find that the coming slides, all of them are most of them, I mean, not all of them, are revision of what I gave you in the 3 videos I uploaded in the Google Classroom. And that's why you have to hear the 3 videos before going on with this slides, because whatever inside the video, you will find them illustrated here in the next few slides. And this sequential circuit, as from the name, it's actually something that deals with time and we deal with frequency, because F equal 1 over T. Now let me start defining what's meant by sequential circuit. This slide you saw it before, because we are talking about the different types of logic circuits. You know that we have combinational and we have sequential. Combinational is the one you studied before, and and the first thing for it is the two stable. When the two stable is known, which is a relation between in and out, the inputs are known, the output are given, and this is what's called combination. That's why we say it consists of logic gates whose outputs at any time are determined directly from the values of the present inputs. Of course, there is no feedback and no storage element are involved in the combination. This is what we had before in the last lectures. But now I'm going to talk about sequential. Sequential means, as you mentioned in the video, the uploaded video in the Google Classroom, you find that this involves loops. Loops means something related to time, because at a certain time it will give a value and another time another value and so on. So actually the sequential circuit depends on time as well as frequency, because F equal 1 over T again. So it involves, because as long as we are talking about the dynamic changes, so it involves storage element, which means something like flip-flop. Flip-flops mean you are flipping from one value to another value, and of course for digital it's a 0, 1, 1 to 0, 0, 1, 1 to 0, 0, 1 to 1 to 0. It actually be square wave from zeros and ones. If 0 goes to 1, and 1 goes to 0, and this will be, as long as it's flipping from 0 to 1, we call this one flip-flops, and this is it's a way of storage elements. The outputs of a function of input, the outputs of this type of hardware is a function of inputs, the combination input, and the state of the storage element. So actually, in the past and in the combination circuit, the output is a function of inputs only. But here, it's a function of inputs and the state of the storage element, and the state of the storage element is a function of the previous input. So this means that I have to have information about the previous input in order to go to the next state. So actually what we have here as a counter, say if you have a counter that goes from 0 to 1, so present state is 0, next state will be 1, and when you go to 1, you're waiting for some signal to tell you go from 1 to 2, as in 2 to 3, 3 to 4. So we have something called present state and something called next state. So that's why we are saying that outputs are a function of inputs and the state of the storage element. And actually, as long as you are depending on time, so the circuit behavior must be specified by a time sequence of inputs and internal state, because it depends upon signals, it depends upon timing, it depends upon frequencies. That's why we say the behavior is not that must be specified at a certain time. This is what we're going to discuss in the next slides. This slide here is exactly the same like the one I discussed with you in the previous slide, but actually here with graphics. As you can see, for combinational we have n inputs, m outputs, and 2 power n possible input combination, and 1 possible output for each binary combination of input values. This is as long as the two stable is known. This everything here is in clear and known. If we're talking about the sequential, you can find here we have a feedback. Feedback means we have the input and output like before the combinational. So the input and output, these are combinational circuits, exactly the same, but not, we don't have here now the two stable. We have something called state table, because we have here next state and present state. Present state is known for you because this is what you see, and next state, what will happen after the combinational circuit will perform, and then the storage element will tell you when you can see the next state will be changed to present state. This is actually the sketch of the sequential circuit, and I'm going to discuss with you in the next slides what's meant by a state diagram, a state table, because in the combination we call it this table, but here we call it a state table because you have inputs, you have outputs, and you have next state, you have present state, so actually something is related to time, so you have to understand that input and outputs are known, but for us we have next state and present state depends on the storage element. So because the storage element actually will give you when, and if you can see, you can change the next state to present state in order to go inside the combination, and then be next state again, and next state goes into storage, and so on. So this loop here is actually give you the timing and synchronization for the sequential circuit. As you can see here, the outputs are function of input and present state, and also the next state with the partial output is a function of input and present state. And this will be clear in the next slide. Based on the two slides I mentioned in the previous two slides, we can say here sequential circuit is specified by time sequence of inputs, outputs, and internal states. It contains memory and thus can remember the changes of the input signals and that occurred in the past. Also, inputs for the sequential circuit are functions of external inputs and the present state of the storage element. Both external inputs and present state determine the binary value of the outputs and the condition for changing the state of the storage state. This means here the output is a function of external input and the present state, and next state is a function of external input and present state. This is actually illustrate what we mentioned in the previous two slides. As you can see here in this slide, the sequential circuit we have two types of sequential circuits. We have synchronous and asynchronous. Synchronous means that it is a system whose behavior can be defined from the knowledge of its signals at discrete instant of time. This means if you have, say, you power on your computer. The first thing that the system will see is that to make sure that the screen and keyboard and mouse and motherboard and every controller and memory and all these important components are working at the same time. Synchronized means they should work simultaneously at the same time with the same clock, because you cannot have any delay between any of these items, otherwise you can have a fatal or you can have an error with your computer. So all of this should be synchronized and be open whenever you touch the power on. All of them should be working at the same time. This is what's meant by synchronization. Asynchronous is a system whose behavior depends upon the order in which the inputs change, and the state of the circuit can be affected by at any instant time. This means you have a printer attached to your computer. The computer will not check if the printer is on or off. It will only check with the computer, with the printer, when you demand, when you ask to print a page. This means that this device here is not is as important as the main components, and what's happening here, whenever you need to use it, you will just send an order to the printer to work. This is what is called asynchronous, because it depends upon your needs. If you need to use it, you're going to use it. If not, it doesn't matter. The computer will never give you an error unless you are looking for that printer or for the modem or anything attached to your computer. This is what I meant by asynchronous. Asynchronous means at the time that clock is just for to open the system, but whenever you need the other one to be open, you have to ask for it in order to activate the other devices attached to your computer. This is asynchronous and asynchronous. This is the definition of synchronization and as a asynchronous device. So if you can say here, an asynchronous sequential circuit may be regarded as combinational circuit with feedback. Just the system may operate in an unpredictable manner and sometimes may even become unstable. And this is what meant by asynchronous, because it's waiting for something, and if this is not available, it will give you a instability in your system. The various problems encountered in asynchronous system impose many difficulties on the designer, and for this reason they are seldom used. You don't use asynchronous too much because of that. A synchronous sequential circuit employs signal that affects the storage element only at discrete instant of time, as synchronization is achieved by timing device called clock generator. So as I mentioned, clock, which means a square wave, goes from 0 1 1 to 0 0 1 1 to 0, that produces a periodic train of clock pulses, and we call this square wave. A square wave, which means 0 goes to 1, 1 goes to 0, 0 goes to 1, 1 goes to 0, and this is what will control your storage element. So here only again asynchronous is not used a lot, but asynchronization is used a lot because of the reasons mentioned in this slide. Actually, the clock pulses are distributed throughout the system in such a way that storage elements are affected only upon the arrival of each pulse. The output of the storage element can change only when clock pulses are present. This means that you have to have a clock, and this clock will be described in the next slide because it depends upon going from 0 1 or going 1 to 0, which one it will affect your device. This is going to show you in the next slide. The storage element employed in clocked sequential circuit are called flip-flops. Flip-flops because it goes from 0 1 1 to 0 0 1 1 to 0, so it is going from value to another value and so on. This is what we call a square wave as mentioned in previously, and we'll mention in the next slide also. A flip-flop in binary storage devices, a flip-flop in a binary storage device capable of storing only one bit. When you talk about a flip-flop, you can store only one bit, either 0 or 1. So it stores only one bit of information. When a clock pulse is not active, the feedback loop is broken because the flip-flop outputs cannot change even if the outputs of the combinational circuit change in value. Just as the transition from one state to another to other occurs only as a predetermined time interval dictated by the clock pulses. This means that, that's what I mentioned before, if you go to the block diagram of the sequential circuit, you will find that the next state are waiting for the storage element of the flip-flop in order to give it order to be changed from next state to present state. And that's why it says here, when the clock is not active, it will never, even if you have the combination circuit, it will not work unless the storage element will give the order for the next state to change to present state, because you know the output is a function of inputs and present state, and the next state is a function of inputs and present state. This is active dependency, and this is explains what is written here, and I'm going to show you by graphics in the next slide. This slide here illustrates what I mentioned in the previous slide by graphics. As you can see here, I'm talking about in a combinational circuit, we have inputs and outputs which are purely combinational, and we have the next state going inside the flip-flop with our storage element, and we have a clock pulse which is a square wave, and I'm going to describe what's meant by square wave in the upper in the upper three graphs in this slide. But let me first of all talk about what's the scenario about what's going on with this graph here. So whenever the clock pulse goes inside the flip-flop, it will give order to the flip-flop to accept the next state and change it from next state to present state. So thus the loop is going like that. Next state goes inside the flip-flop, waiting for the clock pulse to give it an order in order to go to change to be present state, and then goes inside the combinational to be changed again to next state, and then waiting for the flip-flop again for the clock to give it an order, and so on. So as you can see in the upper three graphs here, first of all, a square wave is not purely a square wave, because as you can see, the square wave it goes from 0 to 1, it doesn't go abrupt 0 to 1, it goes exponential, and you have some kind of oscillation, and then it goes to steady state. So there's something called setup time or delay in order for the system to be asserted that it is 0 or 1. But in this course, I'm going to ignore that and assume that 0 goes to 1, 1 goes to 0 abrupt. But actually in real life, it's not like that, as you can see in the left graph. The two other graphs you can see here, the flip-flop will accept either the positive edge or negative edge, which means positive edge, if you go from 0 to 1, this will give you the order for the flip-flop to accept and then change next state to present state. This is what the positive signal. The negative edge triggered means when the signal goes from 1 to 0, the flip-flop will go from 1 to 0, the flip-flop will order to next state to be changed to a present state. So this means here the square wave, we are not going, we have to accept that if it is positive edge, for each positive edge when the clock goes from 0 to 1, the flip-flop will give order to the next state to change present state. So this means that it will wait a t, the time period is t, it will wait for t period and then give you the order again, and so on and so on and so on. So actually in between the two positive edges, then nothing will happen to the flip-flop until it is activated again. That's why the combination circuit will do nothing until the flip-flop goes from one positive edge trigger to the second positive edge trigger to the third positive edge trigger and so on. If it's working with a negative edge trigger, it will do the same, but now it was when the one goes to 0, and this is what we call negative edge trigger. To differentiate between positive edge trigger and negative edge trigger, can you see here in the graphs in the upper two pictures that the clock sometimes it has a bubble and does not have one, the other one doesn't have a bubble. If it doesn't have a bubble, this means positive edge triggered. If it has a bubble, it means a negative edge trigger. So actually the flip-flop will work only either positive edge triggered or negative edge triggered, and this is what's meant by the flip-flop is waiting for the clock to be active in order to change next state to present state. I believe this will be for you understandable, and if you have any question you can ask me. Remember that also when we discussed in the video that the flip-flop circuit has two outputs, Q and Q bar. One of the normal values is Q, and the other for the complemented value of the bit that is stored in it. So if we have here Q and Q bar, so you have to remember that we have the output of each flip-flop is only one bit, but actually we have Q and Q bar present for outputs for that flip-flop. Let me start here with the latches, which I discussed with you in the videos I uploaded in the Google Classroom. Actually, a flip-flop can maintain a binary state indefinitely as long as power is delivered to the circuit until directed by an input signal to switch state. So actually, whenever you have a value inside the flip-flop, as long as there is no clock, there is nothing in it, it will keep the value inside it until it changes. If you want to change it by putting another input, and the clock will accept that and give change the value of that flip-flop. Latches are the basic selected for which all flip-flops are constructed, and these latches we discussed in the video, and I'm going to repeat it here in order for you to refresh your memory and find out what is the value and what is the effect and what is the functionality of each latch. And as I mentioned in the video, we have 4 different latches: SR and JK and T and G, and I'm going to discuss each one individually in my next slide. In this slide here, we're going to start with the SR latch with NOR gates. As you can see here, we have 2 NOR gates back to back. Back to back means what? We have a feedback. Can see that Q goes back again inside the lower NOR, and Q bar goes back again inside the upper NOR, and you can see we have here S and R inputs. The S and R, why we said this S and R, S stands for set and R stands for reset. If you go through the state table means that if the value of SOR equal a certain value, Q next will be as shown in that state table. That's why we say here when S equal to 1 and R equal to 0, we find that Q is 1 because 1 is a dominant on the NOR gate. When having 1 on the NOR gate, you know shows that irrespective of any other input, the output will be 0. So if S equal to 1, this means the Q bar will be equal to 0, and then 0 goes with 0 will give you 1. This means that Q equal 1. This we call it a set state. So whenever S equal to 1, R equal to 0, you are inside what's called the action is set state. If you apply after having the initial value 1 to 0, S1 and alpha 1 and alpha 0 also, this means that if you apply 0 and 0, this means you're going to have a no change situation, because 0 0 after having 1 and 0 will keep the value as is. 1 is still 1 and 0 is still 0, and this is what we call no change a situation. After that, if you have S equal to 0 and R equal to 1, you will get that Q equal to 0 and Q bar equal to 1, because the 1 on R will reset the Q, and this is what we call the action will be reset state. And if you apply again 0 and 0, this means no change, the 0 stays 0 and 1 stay 1 until further changes on the S and R. As you can see in this state table, 1 on 1 is forbidden. You cannot use 1 on 1 because 1 on 1 means q equal q bar, and this is not valid, of course, and this is what we call undefined state. This is a property of the NOR gate, and this is the definition, the main definition is the reference of our flip-flops in order to understand you have set, reset, and not change states. This is actually the SR latch with the NOR gate. In the other next slide, we're going to discuss the same scenario, but with a NAND gate instead of NOR gate. If you apply the same scenario with the two NAND gates, as you can see here, we have two NAND gates back to back again instead of NOR gates, but actually you will find that whenever S equal to 0 and R equal 1, you will get set state with Q equal 1 and Q bar equal 0. And if you have 1 on 1, this is a state of no change, because 1 on 1 on NAND gate will never affect, because the NAND gate is affected by 0. The dominant is 0. Whenever you have 0 on a NAND gate, you get 1 on the other side, irrespective of the other inputs. This is actually opposite of what is happening for the NOR gate. So again, if you have here, the no change here is 1 on 1 instead of 0, 0. And also the 0 on S and R equal 1, this will give you set state. Again, if you change S equal 1 and R equal 0, you will end up with reset state, which means Q equal to 0. And 1 on 1 again is no change. And the forbidden state is 0, 0, because 0, 0 will give you Q equal Q bar, and this is not acceptable, it's undefined. So actually you can see here the definition of the NAND gate is completely opposite to the definition of the NOR gate. So we need actually to change everything in order to have only one definition for all. You cannot have two definitions for a certain functionality. So actually I have to adapt to the definition of the NAND gate to comply with the definition of the NOR gate. As long as it is opposite, so then you can say you can use S bar or R bar instead of S and R. But actually this is not acceptable again, because you cannot have a device where you are using NOR gate, you can say we have S and R, and when you are using NAND gate, you are using A, you can say I have S bar and R bar. You cannot use different names for the same A configuration. So this is what we're gonna solve and resolve in the next slides. So actually here, in order to have the SR latch with NAND gates to comply with the definition of the NOR gate, we have to use S bar and R bar, and this will make us change some in the design of the NAND gate latches, and this one I'm going to discuss with you in the next slides, because everything here is opposite. Notice that the S input in the SR latch must go back to 0 before any other changes can occur. This is what we call the no change situation, or no change state. There are two input conditions that cause the circuit to be in the set state. The first is the action that must be taken by the input S to bring circuit to the set state with S equal 1 and R equals 0. The second is the removing of the active input from S, leaving the circuit in the same state with A when is a no change state with S equal R equals 0. When S equal R equal 1, no states latch, both outputs go to 0. This produces an undefined state, and it also violates the requirements that output A, Q, and Q bar be the complement of each other. This is actually we discussed when we talked about the NOR gate latch, but I'm just repeating it here for you to remind you. Also, when comparing the SR NAND latch and the SR NOR latch, we note that the input signal for the NAND required the complement value of those used for the NOR latch, which means they are opposite to each other. Because of the NAND latch requires a zero signal to change its state, it is sometimes referred to as an R bar S bar latch. The bar above the letter designates that the fact that the inputs must be in the complement form to activate circuit, and this is what we discussed when we talked about the NAND gate previously. And now I'm going to solve this problem by giving you another configuration for the NAND gate in order to comply exactly with the SR definitions as we discussed before. Now to solve this problem, as you can see here, we need S bar and R bar. Instead of doing that, we are going to use the property of the NAND gate. Property of the NAND gate is what? If you have a NAND gate and you have 1 with any other variable, 1 with anything will give you what? Will give you the bar, and this is what happened here. We have extended the diagram in order to have 2 extra NAND gates, as shown in this figure. But here I have another control now. This console is called C. C for us is what we call here as controlling the whole circuit in order to make it work or doesn't work. If you remember, we talked about the clock which will give you the flip-flop, the order to accept the input or not. This is actually one way of making the flip-flop or the latch accept the input or not, because if C equal to 0, this means that you have 1 and 1. This is not changed. Actually, the system is blocked. So irrespective of the value of S and R, when C equal to 0, we have a no change, and this is actually controlling the flip-flop. When C equal to 1, the flip-flop will act based on the value on S and R, and this is what we call here a control variable in order to make the flip-flop work or does not work. This is what we call here a level triggered latch. Level triggered means what? Whenever SC equal to 0, there will be no change, the system is blocked. Whenever C equal to 1, the system will work properly and give you the results. So as you can see here, 1 when C equal 1, which means that I'm now going to have S bar and bar, and this is actually resolve the problem of the NAND gate and will give you exactly the same scenario as the NOR gate, and actually this comply with the definition of the NOR gate, and this is how we solve the problem, and we have now one definition for all. When S equal 1 and R equals 0, you will get set. When S equals 0, R equal 1, you will get no reset, and when S equal R equals 0, you will get no change, and this is exactly what we defined before for the NOR gate. And as you can see here in the table, when C equal to 0, irrespective of value of S or R, there will be no change, and when we have C equal to 1 and C and R are 0, 0, you get no change, and we have C equal 1 and we have S equal 0 and R equal 1, we get reset state, and if C equal 1, S equal 1 and R equal 0, you get reset state, and when C equal 1 and S equal R equal 1, this is undefined or undetermined state, and this is exactly the definition. So now this is how we made the NAND gate talk the same way as the same reference and the same scenario as the NOR gates. The NAND gates exactly now have the same definition for the NOR gate, but here I have an extra two NAND gates in order to comply with the definition for both. So for both of them are SR latch, and they both follow the same conditions. When S equal 1, R equal 0 is set. When S equal 0, R equal 1 is reset. And when S equal R equal 0 is not changed, and the undefined state is S equal R equal 1. Note that we have an additional control input which determines when the state of this latch can be changed is added to the basic SR latch to improve its operation. The control input C acts as an enable signal for the other two inputs, as I mentioned in the previous slide. Based on the SR latch, we are going now to introduce another latch which is called the D latch. The D latch, as you can see here, we have short-circuited the S and R with an inverter as short-circuit and NAND. So as you can hear, I've added an extra NAND here, but short-circuit, which means that it's an inverter. So actually, we have removed S equal R from our system. There is nothing called now S and R, and you're going to ask me, where is the no change? I will tell you the no change comes from the C, because the C here, when C equals 0 is not changed. When C equals 1, the system will work as shown here. But this is a very interesting thing about this D latch. As you can see here, is data in, data out, because what is happening when C equal to 0, irrespective of value of D, this will be no change. But when C equal 1, you will find that when D equals 0, the system will reset, which means 0 equals 0. And when D equal 1, the system will reset. This means whatever is the D input is, the output will be the same like D. So Q equal D exactly when the clock accepts and gives the order for the future to work. So actually this is what we call data in, data out, and this is a second definition of a latch. It's called D latch or D flip-flop. So actually what we have here, when it is with clock, it's flip-flop. When it is without clock, we call it a latch. So actually what we have here, we have SR latch attached to it, a short circuit between S and R, and with A you have constructed what's called the D latch. Okay, the D latch is data in, data out. Just one way to eliminate the undesirable condition of the indeterminate state of the SR latch is to ensure that the inputs S and R are never equal to 1 at the same time. This is what happened with the D latch. With the D latch, actually, as you can see, we removed S equal R from our equation. As long as the control input is at 0, the cross-coupled SR latch has both inputs at level 1, and the circuit cannot change regardless of the value of G. So actually, as you can see here, that we have used the G flip-flop in order to avoid or to remove the indeterminate state, and at the same time we are using the C as a condition for the no change or making the circuit work properly. Another way to solve the problem of S equal R equal 1 is to use what's called the JK flip-flop. The JK flip-flop, actually J stands for S and the K stands for R, so J is set and K is reset. And as you can see from the graph here, and we describe this JK flip-flop in details with the 3 videos we gave it to you in the classroom, the Google Classroom. Before we have make a trace for the signal JK to go to give you Q and Q bar, and we ended up with the A following state table. But as you can see here, J has Q bar feedback with it, and K it has Q feedback with it. So we have another feedback here from Q and Q bar. Q goes with K and Q bar goes with J, and if you place a signal, you will find out you will end up with the A functionality as shown in this table. When C equal to 0, of course, irrespective of the value of J or K, it will not change. If C equal to 1 and you have J equal K equal 0, we will get the state of no change. And with C equal to 1 and J equal 0, K equal 1, you will get the reset state. And when C equal to 1 and J equal to 1 and K equal to 0, you will get set state. And now as a new thing, when C equal to 1 and J equal K equal 1, here you get something called toggling or complement, which means Q bar will be swapping with Q. So we have Q bar instead of Q and Q instead of Q bar. This means you have something called the complement of the value of what we call here toggling. So actually here we make advantage of having J equal K equal 1, because J equal K equal 1 gives you here value, but whenever we talk about the SR latch, when S equal R equal 1, we got a problem. But here now we have used and make use of the 1 and 1. So actually when J equal 1, K equal 1, we have something called toggling or complement of the function. Toggling or complement means Q will go instead of Q bar, and Q bar will go instead of Q. So actually I'm swapping the position of Q and Q bar, and this is what we have here. It's the third latch and the third flip-flop is called JK flip-flop. And discuss this in details in the video if you want to go back to the video. The last type of a flip-flop or D flip-flop, also of latches, actually we have what's called the T flip-flop. The T flip-flop, as you can see here, we have short circuited the J and K. So actually there is no J and K here, they have only T, which means that you have either no change or toggling. This is the fourth flip-flop for a defined for your circuit. So as you can see here, when C equal to 0, irrespective of value of T, does not change. But when C equal to 1, you find when T equals 0, you get no change. When T equal 1, you get only the complement or toggling of the function. So that's why, because I have removed J equal, J does not equal K, we have only J equal K, because it's pure short circuit between J and K. So this is what we call T flip-flop. Now we have 4 flip-flops, or the latches. We have the SR latch, the SR flip-flop. We have the T latch or D flip-flop. We have the JK latch or JK flip-flop, and we have the T latch or T flip-flop. I mentioned T flip-flop or latch. It means that whenever you have a level 3, there is a latch. Whenever you have clocked input, it is a flip-flop. But both have the same functionality, the same twist table, and the same state table as shown in the slides. This table here summarizes all the characteristic table for the 4 flip-flops, the SR, the JK, and D and T, and the equations. Actually, as you can see here, SR flip-flop, you can see whenever S and R are known, you can predict what is the next state. Actually, Q of T plus 1 means Q next, and Q of T means QA present state. So Q of T plus 1 again is next state, and Q of T is A present state. So whenever S equal R equals 0, you will get a Q of T plus 1 equal Q of T, which means no change. When S equals 0, R equal 1, you will get 0, which is reset. When S equal R and equal 1 and R equal 0, you get Q of T equal 1, which is set. When S equal R equal 1 is not applicable, which means an indeterminate state. For the JK flip-flop, as you can see for the table for the JK, you have when JK equals 0, you have Q of t plus 1 is Q of t, which is not changed. When J equals 0, K equal 1, you get Q of t plus 1 equals 0 with the set. And when J equal 1 and K equals 0, you get Q of t plus 1 equal 1 with the set. When J equal K equal 1, you get A is a complement, which means Q of t plus 1 equal Q of t bar. For the D flip-flop here, as you can see from the table, when D equals 0, you get Q of t plus 1 equals 0 to the set. When D equal 1, you get Q of t plus 1 equal 1 with this set. This is actually the characteristic table of D. For the T flip-flop, you have when T equals 0, you have Q of t plus 1 equal Q of t with no change. When T equal 1, Q of t plus 1 equal Q of t bar, which is the complement of the function, and this actually summarizes the characteristic table and the equations for the 4 flip-flops as shown here, and this is you have to memorize and have it in your mind because this is the characteristic table. If the flip-flop is known, you can predict what is the value of the Q of t plus 1, which is Q next. So actually based on the characteristic table given in the previous slide, the analysis procedures, you have to obtain the binary value of each flip-flop input equation in terms of the present state and input values. Use the corresponding flip-flop characteristic table to determine the next state. So actually this is the procedure. As long as you have the characteristic table, you can predict what is the value of the next state as mentioned in the previous slide. Actually, the characteristic table are a shorter version of the truth table. It gives for every set of input values and the state of the flip-flop before the rising edge of the rising edge means the positive edge of the edge the corresponding state of the flip-flop after the rising edge of the clock signal. So you have to have the input asserted before the clock is giving you the order to move the input to the output. So this is actually what we get from the characteristic table. By using the K-map, you can derive the characteristic equation for each flip-flop. So actually here, this is just description that you have to follow the clock because the clock is the rising edge of the input should be active before and the rising edge of the clock signal is there because you have to have the input asserted in order for the clock to give you an order to move from in to out. So you should have the right input to have it on the right output. We mentioned before the characteristic table for the flip-flops where we have 4 flip-flops JK and SR and T and D, and we mentioned the characteristic table that if you know the values on JK or SR or T or D, you can predict what is the value of Q next, which is Q of T plus 1. And this actually I'm giving you example here on the left corner of the slide. I'm giving you the characteristic table of the JK flip-flop. Now we have another tables which you're going to use, make use of it to solve your sequential circuit. It's called the excitation, the flip-flop excitation table. Let me start with the JK flip-flop excitation table because this is actually the example I'm going to give you in details, and then you have to follow the same scenario for the SR and D and T. As you can see here, we have in this table Q present and Q next are known. What is the application of that? If you have a counter, you know exactly you are starting from 0 and go to 1. So 0 is your present state and 1 will be named next. And then you're going from 1 to 2. 1 will be the present and a present state, and then the 2 is next. So actually, the present state and next state are known. So we need to find out how to put the values on JK or SR or T or D in order to get such a procedure and such a functionality. So actually here the unknown are the flip-flops, the other one with the unknown is the Q next. So the characteristic table is used when the unknown is the next state, while the excitation table is used when the flip-flop status ZK and R and T and G are not known. So actually let me now give you a way in order to configure what is the excitation table for the JK. As you can see here from the table, we have Q of t, which is the present state, and Q of t plus 1 is the next state. So when Q of t plus 1, 0, 1, 0, 1, and you have Q of t double 0, double 1, so you see the first row. The first row we have Q of t is 0 and Q of t plus 1 is 0, which means 0 goes to 0. This goes to 0. If to go back to the characteristic table, you find this comply with no change and reset. So we have no change and reset. This is a state of the A that will give you 0 goes to 0. And if you go back to the value of J and K, you find J is always 0, while k changes from 0 to 1. That's why we have j equal to 0 and k equal don't care, x يعني. Okay, and the second row, if 0 goes to 1, which means here 0 is present state and 1 is the next state, this will go with a in the table, characteristic table, that is set or complement. Set or complement, which means j equal 1 all the time, while k is a changing value, so we have k as a, as don't care here, as x. But when we talk about the third row, with q of t equal 1 and q of t plus 1 equals 0, which is 1 goes to 0. When you say 1 goes to 0, it says here what? It says here either it is complement or reset. Complement or reset, which means that k is always equal to 1, while j is changing from 0 to 1, so j is don't care. So we have j don't care and we have k equal to 1. The fourth row, where q of t equal 1 and q of t plus 1 equal 1, this means the 1 goes to 1, this means no change or set. No change or set معناها ان j equal don't care and k equals 0. This is how we reconfigure the accession table for the jk flip-flop. We are going to use the same scenario in order to configure the SR flip-flop accession table and D flip-flop accession table and T flip-flop accession table as shown here in the in this slide. But the very interesting thing that if you watch the D flip-flop accession table, you find D is always equal to the next state. So whenever you know Q of T and Q of T plus 1, D is always Q of T plus 1 as shown in this table. Also for the T flip-flop, you can find out that T is equal Q of T XOR Q of T plus 1. So this is a very interesting observation. But actually, if you want to build this type of accession table, you can configure it from the characteristic table directly. There's no need to memorize these tables. And as you can see here, you have two types of tables. One is excitation and the other one is the characteristic. The characteristic is used when you know the flip-flop status and you need to find out what's Q of T. Q of t plus 1, which is the next state. And the excitation table is used when you know Q of t and Q of t plus 1, you know the present state and next state, and you need to configure out what is the status of the flip-flop, the JK and SR and D and T, and these are the two tables used in order to solve any type of a sequential circuit, as we're going to show you in the next slides. Just from the previous slide about the excitation table, we can say that the excitation for each flip-flop is used during the analysis of sequential circuits. It is derived from the characteristic table by transposing input and output columns. Also, it gives the value of the flip-flops inputs that are necessary to change the flip-flops present state to the desired next state after the rising edge of the clock signal. Note that when I say here rising edge, I mean the positive edge triggered. Okay, and this also with all that, also what I also described in this slide, we already explained it in the previous slide. Given the characteristic table and the excitation table of the flip-flops, now I'm going to show you in this slide how you use when to use the excitation table and when to use the characteristic table, and these two tables are our key for solving any type of sequential circuit problems. As you can see here, we have two tables, one with D flip-flop and the other one with JK flip-flop, and I'm going to show you when to use the excitation table and when to use the characteristic table. The table is composed of, it's called state table. State table, why? Because we have current state and next state. Current state is a present state, which we have A capital and B capital. These are the Q's of the flip-flops, and A next and B next are the next values for the Q's of the flip-flops. We have also added here external input I and the external output Y. The external input and the external output are purely combinational. They are used for either enable indicator or something like that for any circuit you're going to use. Because as I mentioned before, the sequential circuit is composed of partially goes part is combinational and the other part is sequential. For the combinational part, we have external input and external output, and as you know, the external output is function of external input and current state, and the next state also is a function of external input and the current state. Let me now tell you how to solve the problem like that. If you have the table like that, sometimes you have this one is unknown. So actually we have the next state is unknown. When the next state is unknown, we use the characteristic table in order to find out what is the next state is. So this is actually how we one type of a problem for the sequential circuit. If you know if the next state is unknown, you use the characteristic table in order to find what D is, and then you find the corresponding the present state is value, and then you find what's the next state based on the characteristic table. The other type of problems, if you have the flip-flop status is unknown. If the flip-flop status is unknown, we use what's called the excitation table, because as long as present state and next state are known, we can use the excitation table to find out what is the value of your you can put on your flip-flop. This is two types of the problems that we can face in the sequential circuit. Now let me show you how it's done. Assume that for this table here, for the JK, we have the present state B equal to 0. And then the next state A is known, and this one I'm talking about present state is known. So if the present state is 0, what's going to happen? So if the present state is 0, what you do, you'll find that's the value of JB and KB. From where? From the action table. If you go to the action table shown in the left corner, you find that whenever 0 goes to 0, this means a j equals 0 and k equals x. In the same way, what you're going to do is you go to the second one, 0 goes to 1, and then you go to the back to the table, you find that 0 goes to 1 means jb equal 1 and kb equal x, and so forth. And so this is the way you are solving the problem. After doing that, you're going to have a full key maps for JA and KA and JB and KB, and you find the hardware. And when you find the hardware, you can draw the complete circuit, as you're going to show you in the examples coming next in next slides. So this actually this slide here give you an idea of what's going on and how to solve the problem. For sequential circuit, we have two types of problem, as I mentioned before. One problem when the next state is unknown and you are going to use the characteristic table, and the other problem if is a JK or D or whatever are unknown, and you can use the excitation table to solve the problem. And I'll show you now. This slide give you most of the problems you're going to face to solve any sequential circuits. I mentioned in the previous slide about the state table. Now, in addition to graphical symbols, tables, or equations, flip-flops can also be described uniquely by means of state diagram or state graphs, in which case each state would be represented by a circle, and a transition between state would be represented by an arrow. This I'm going to show you in the next slide by another way to represent the sequential circuit by using graphs and using what's called a state diagram or state graphs. Besides the use of the state table and the equations and all what is representing a sequential circuit, we have here going to give you another solution for the sequential circuit, which is state diagram. State diagram for various flip-flops. As you can see in this slide, we have two flip-flops, the SR flip-flop and JK flip-flop, and as you know, for one flip-flop, we have only two states, either the Q equal to 0 or Q equal to 1. So I have one circle for Q equal to 0 and another circle for Q equal to 1. And then we have a directed arrow which will show you the transition from 2. So if you want to go from 0 to 0, you find that you have to have SR equals 0, 0 or 0, 1. And if you want to go from 0 to 1, you have to have SR equal 1, 0, which means S equal 1 and R equal 0. If you want to go from 1 to 1, you have SR equal 0, 0 or 1, 0. If you want to go from 1 to 0, you have to have SR equal SR equal 0, 1. And also I can show you that what is done here. You have two circles for the states, and you have a directed arrow. You can write on top of the arrow the flip-flop status, or you can put here the external input and the external output. External input over external output, as we're going to show you in the next examples or slides after that. Also, we have as long as here we have one flip-flop, this means that I have I have two states, Q equal to 0 and Q equal to 1, so I have two circles. But if I have two flip-flops, this means I have four states, which means 0, 0, 0, 1, 1, 0, 1, 1. So I mean I have four circles. If I have three flip-flops, this means that I have 8 circles, starting from 0, 0, 0 up to 1, 1, 1, and so on. So for the JK flip-flop now in the lower part, we have JK flip-flop. We have two states and Q equal to 0 and Q equal to 1. If you want to go from 0 to 0, you have to have JK equal 0, 0 or 0, 1. If you want to go from 0 to 1, you have JK equal 1, 0 or 1, 1. And if you want to go from 1 to 1, you have JK equal 0, 0 or 1, 0. If you want to go from 1 to 0, you have JK equal 0, 1 or 1, 1. This is actually what is the state diagrams for both SR and JK flip-flops. This slide here, I'm going to give you also the state diagram for the G flip-flop and the T flip-flop. As you can see here, the same sequence. We have two states, Q equal to 0 and Q equal to 1. And the directed arrow will give you the value of G and the value of T for each one of them. This is actually for the 4 flip-flops. Now we have what's called the state diagram for the 4 flip-flops. Let me here summarize what's meant by the state diagram. The state diagram can be obtained directly from the state table, because in the state table each row will give you all the information required to draw the state diagram. The state is represented by a circle, and the transition between state is indicated by directed lines connecting the circles. The directed lines are labeled with two binary numbers separated by a slash. The input the input value during the present state, and the second is the output value during the present state. And this is okay in over out. Or you can write down, or you can label the directed arrow by the status of the flip-flops. Some state same state can represent both the source and destination of a transition. Each state can be thought of as the time interval between two rising edges of the clock signal. This is a description for what's meant by the state diagram. In this slide, I'm going to show you by graphs what's meant by the state diagram. As you can see here, we have two states, Q equal to 0 and Q equal to 1, and each state is enclosed inside a circle. So we have two circles here, one for Q equal to 0 and the other one Q equal to 1. And as mentioned here, we have directed arrows. The arrow can go from one state to another, or for the state for itself. So actually we have a directed arrow, which means the transition from present to next. Okay, and also we are labeling the directed arrow with input over output during the present state. So make sure that this is actually the values are during present state, not during next state. Next state is nothing for us. Next state is only an indicator to use it if you want to find towards the states of the flip-flops, but only the reference is our reference is the present state. So we only deal with present state. So actually say input and output during present state. Don't forget that. And at the same time, we can put also during the present state, we can put what is the status of the flip-flops at that time. So actually, on directed arrows, you can put either input over output, or you can put the status of the flip-flops, and this is describing what's meant by state diagram by graphs. Now let me conclude with this example. Example here, you should consider a sequential circuit with two flip-flops, JK, A and B. This means that we have JA and KA, and we have JB and KB, and one external input X specified by the following equation. JA equal B, KA equal B X bar, and JB equal X bar, and KB equal A X bar, the A bar X. This is actually, this person is giving you everything. He's giving you the hardware, he's giving you the equations, and everything is given here. So as you can see here, what is required? What's missing here? The missing part here, this means that the J's are known. Q present, of course, will be known, because Q present, this is actually what we have in our hand. And what's missing is Q next. So he's asking you to find out what is Q next is equal to. So actually in this problem, this person is giving you the hardware and equations from which you have to construct the state table and the state diagram and find out what it looks like. Actually, this slide here show you exactly the hardware and the equations. And as you can see, he's giving you everything. He's giving you J and A and KA and JB and KB, and the diagram which you follow and get any information you are looking for. So what we are looking for here, we know that we have a present state, and we need to find out what will be our next state. And this is what I'm going to do in the next in the solution. I'm going to show you how I'm going to construct the state diagram and the state table for this problem. In this slide, we are going to solve the problem by constructing the state table, and then we're going to construct after that the state diagram. But as you can see here, the state table is constructed from the present state input, and we have next state, and we have the status of flip-flop. As you can see in this problem, we don't have external output. So first of all, we're going to put the present state and the input. The present state and the input, you can see here the A capital, B capital, and X. We consider the same standard way we used to do it before. So we have three inputs, which means that we have 2 power 3 of the combinations, and we start with the first column 0 1 0 1 0 1 0 1, second column double zeros double ones, and the third column will be 4 0 4 ones, and actually this will be the initial value for to use in order to solve the problem. As you can see here, the input X is external input, and this is combinational, and the present state is your sequential part for A and B for the flip-flops. Now, by using the equations given by the problem, you can find out what is JE equal to, what is KA equal to, what is JB equal to, and what is KB equal to. So you have by using the equation, you will get the values for JA, KA, JB, KB, and this is actually now is known for you. And the J and K is unknowns, and we have the present state is known. So actually, we can use to solve the problem. The only missing part is your next state. In order to get the next state, we have two tables as I mentioned before. We have the JK characteristic table, and we have also the JK extension table. But as you can see here, as long as the next state is missing, we're gonna use what? We're gonna use the characteristic table in order to find out what will be the next state. So actually, by applying the characteristic table over the present state and find out, you can find out what's next is equal to as shown in this table now. So by taking A as your as the present state and find the status of JA and KA, you will get a next. And by taking B as the present state and you use JB and KB to find out what will be your B next. And this is how we constructed the truth table, the state table as shown in this slide. Now I need to draw the timing, the state diagram. The state diagram, as long as we have two flip-flops, this means that we have 4 states 0 0 0 1 1 0 1 1, and you start with row number 1. As row number 1, you find you have here 0 0. 0 0 goes where? 0 0 goes to 0 1. This means that this state goes to the other state 0 0 to 0 1 when x equal to 0, and this is what will be labeled for the directed arrow. We will have x equal to 0 over this arrow, or you can have JA equals 0, KA equals 0, JB equals 0, KB equals 0. So actually you can have a state diagram that drawn like that. This is for the first row, the second, until you finish all the states, and this is how you construct the state table, the state diagram from the state table, and we're going to show you the state diagram in the next slide. So to summarize what we did in the last slide, we have to the steps for solving the problem. We find JA, KA, JB, KB from the equations, and then we find the next state from the corresponding J and K inputs using the characteristic table of the JK. This is what we did in the last slide. Now to conclude the problem, we have to draw now the state diagram as mentioned in the state table. The state diagram, we can get it from the state table as mentioned before. And as you can see here, we have 0 0 goes to 0 0 when value of x is 1. And we have 0 0 goes to 0 1 when value of x equal to 0. And 0 1 goes to 1 1 when value of x equal to 0. And so on. This will be actually the 4 states of the flip-flop, because as long as we have two flip-flops, we have 4 states 0 0 0 1 1 0 1 1, and the directed arrow is following what's happening in the state table, and whatever written on the top of the labeling the directed arrow is actually the value of x. So this is actually the state diagram of the example, and this concludes the example given to you.